So it's a great pleasure to be here. It's the best mathematical institute in the world, definitely. Everything works perfectly, and so it's just a pleasure to be here. Okay, so my talk is based on two big papers, pretty long, each of them, and they both can be abbreviated as NTV, but in both cases it means different things. So the first paper is Nazarov, Trail, myself, and it's like published pretty long ago, 10 years ago. And another NTV is and it's only will be published in 2014. But of course, there are preprints on arXiv, and so the main theorem. Well, it's hard to say what is the main theorem. There are several theorems, and they are kind of, the first theorem will be reduced to the second, second to the third, third to the fourth. So the first theorem sounds like that. So suppose you have a function non-zero in Rn plus 1. At infinity, it is 0. And also it's Lipschitz. And also it is harmonic in Rn plus 1 minus a certain compact set. So we should say a couple of things about this compact set to make this problem interesting. So what we will say about this compact set E is that its nth Hausdorff measure is finite. It's this number n is a critical thing, so it's a critical exponent here. It's the right thing to make it interesting. If this thing would be 0, then automatically we will be able to remove this singularity. So harmonic function, harmonic outside of a small set, will be also extendable to the small set. We know that, for example, if it's harmonic outside one point and bounded, you don't even need that it's Lipschitz. It will just erase this point, and then we'll have harmonic function in the whole space, which is 0 at infinity. Bounded, it's impossible because I said that it's non-zero function. So if this guy would be 0, we will erase it, so it's not interesting. So the only interesting case is this one. So this is what we assume. And then the conclusion is the following. The conclusion can be formulated in several different ways. I will formulate it in the following way. There exists a piece E prime of E. It must be a non-trivial piece such that E prime lies on a C1 smooth manifold. So to explain this theorem, let's first consider n equals 1. So we're on the plane. We're on the plane. There exists a harmonic function which is it's first of all function everywhere. It's Lipschitz, and it's Lipschitz everywhere, but it's harmonic outside of some set whose length, H1 is just length, is positive and finite. Then what we say, this is a very complicated set, so let me give you the examples of such sets E. So, well, simplest example, you have a rectifiable curve, and then you take a positive measure, positive length on this rectifiable curve. That's like example of such thing, and that's the simplest possible example. But on the other hand, there is much worse examples. And this is, for example, something like that. You take a triangle, you take 1/3, 1/3, 1/3, and then you leave just these three triangles, and you repeat this procedure. And eventually you will have a counter set, which also will have this property, but which you cannot put on any rectifiable curve. So these sets are called completely unrectifiable. And because dimension here is 1, this is completely 1. You see n is 1, completely 1 unrectifiable thing. And this is a completely rectifiable. So in this situation, the conclusion says that if you have such a situation, Lipschitz harmonic function, harmonic outside of E, conclusion says that E cannot be completely unrectifiable.
So shall I suggest if you define the rectifiability? If you define rectifiability?
Yes. So let me, it's what I wanted to do next thing. So definition. So we already sort of understand what is completely unrectifiable. So let us now make a definition what is completely rectifiable, because this is not a complementary issue. So n-rectifiable set E is, by definition, it's such that there exist gamma m countably many C1 n manifolds such that so this is completely rectifiable. So this is the example of completely rectifiable with n equals 1, in where you need only one gamma. And sometimes you need countably many gammas to scoop it out. So what about the relationship between completely unrectifiable and rectifiable? So here is theorem of Bezikovich. Well, Bezikovich proved it for n equals 1, but it was later extended. So if we have such situation, then this E can be canonically decomposed to completely unrectifiable. Let's call it null, non-rectifiable. Completely rectifiable. And because it's canonical, you should allow for some dust. And what is this dust? It doesn't matter what it is, because its measure is 0. So the theorem which I formulated says that if you have E like in this theorem, then doesn't matter, forget about it. So it cannot be such that R is empty. It should contain some R. Now, we can formulate it a little bit more, maybe understandably. Why piece? Why piece? Why not the whole E? Because nobody said that E is the full set of singularities of our harmonic function. If E is sort of minimal set, if you already extend your function everywhere you can, so E is really the set of singularities of harmonic functions. So it's the support of Laplacian. So there is a Laplacian, of course, at least in distribution sense. So if you take this support of this distribution and you have this extra information that support is the whole E, you can say more. You can then conclude that this E is R, or R plus D doesn't matter. So it means that you can conclude that E is completely rectified. So notice that I didn't assume anything about U, whether it was positive or negative or whatever. It just didn't assume anything. It can change sign, it can be anything. So it's a structure theorem of the set, say, of singularities of Lipschitz harmonic functions. So, okay, so now I won't be able to present any kind of the proof, but I will present several reductions. Well, first of all, it's pretty easy to see that under the conditions of theorem 1, this distribution is actually a real measure. It's because we assume that Hn is finite. This is a very simple lemma. And this is real measure supported so the first reduction is that if you have situation like that, theorem 2 says that if you have theorem 1, if U E as in theorem 1, then there exists another function V, which has the following properties. So V is fundamental solution of the Laplacian. So phi so you take convolve it with certain measure nu, and so first of all, that V has such form. Secondly, gradient V is still bounded. 3, nu is real measure. Real means it's not positive, not negative. It can have positive and negative parts.
You mean it's a Borel measure? You mean it's a Borel measure?
Borel measure, yes. I wanted to emphasize that it's not positive or negative. It doesn't have sign. It's just some measure. So real Borel measure on E. This measure, actually, even its well, same thing. Its total variation is absolutely continuous with respect to h and e. And 5. Well, it is not positive. It is not negative. So in principle, its total mass of E very easy can be 0. But as I said, it's a reduction. So we can reduce it to the case when this is strictly positive. It's not a trivial reduction, but so now the function v is x minus y n minus 1. It's not n minus 2 because my dimension is n plus 1. Now let me write this measure because it's absolutely continuous. Let me write nu, not total variation, by nu itself, like density with respect to this measure, then this measure, dhne. And for brevity, I will always denote this measure by mu. So our function is like that. And now we have to use that its gradient is bounded. So let's differentiate. So the gradient, well, we can just differentiate under the integral sign. And the gradient will be a vector thing. So I will write it as Rn x minus y b of y d mu y, where Rn is the notation for the following kernel. And so we come to the conclusion that we have a real bounded function b with integral b d mu positive. So mu for everywhere except one place will be just this measure, such that this integral is an L infinity on the whole Rn plus 1. Well, to tell you the truth, it's not defined on E. You see, if you integrate, so you're integrating over E, and if you put x also on E, you have something which is not defined. You cannot integrate the kernel of singularity n on the, even on n-dimensional surface you can do that. And this is not a surface, it's just a set. So let's, to be on the safe side, write here that it's uniformly bounded outside of E. So this is the information we have. From this information, we should conclude something about the geometry of E. That piece of E should be put, can be put on a smooth surface.
What is this measure mu? Is that the Laplacian? Or?
Which one? Mu?
Yeah,
No, mu is always this one. throughout the talk, mu, except one place, mu will be just this measure.
I also have a question. So is E assumed to be closed?
Yeah, it's a compact set. It's a compact set, just not to have any difficulties. So, okay, so let's take a look at this claim when n is equal to 1. So on the plane, just on the plane.
It doesn't say what mu is, it suggests it's absolutely continuous with respect to the whole circle.
Yeah, it's easy to see that this Riesz measure of this Riesz, it's not Riesz, right? Is it? Well, it is. It's Riesz measure of this function is absolutely continuous with respect to Hn. It's easy to see that.
So
And
that's
moreover, this B, the density is bounded. So it's not only absolutely continuous, but absolutely continuous but bounded. It follows from the fact that gradient is bounded.
So it is not the Laplacian of u.
It is Laplacian. It is Laplacian of V. This guy is Laplacian. Well, you see, we said that E. Now, well, I wanted to say that if we have U, then we have another V. And this measure will be Laplacian of
Just
V.
take the remaining part out of it and put the measure on this.
You see, the problem that the measure for U, it's a non-trivial measure, of course, but it can have property that if you integrate, it will be just 0, because pluses and minuses will just cancel each other. I don't want it. For some technical reasons, I need, it's not only non-triviality of measure, but that its first moment is positive. And so this is a reduction, just it's not a very big reduction from the existence of U to the existence of V. It's not a big deal. But let's take a look at the case when n equal to 1. So we still can see that a certain action of singular kernel on my function is bounded. So what is this kernel when n equals to 1? So if there are only x1 and x2, and x equal to 1. If z is x1 plus I x2, this part is the real part of 1 over z. And the second item will be the imaginary part of 1 over z. Because the real part is bounded and the imaginary part is bounded, this is a vector kernel, so all items should be bounded. So this plus I that is also bounded. Now this is 1 over z. So we get that on E, we have bounded real function B, and again, mu, remember, it's always the same thing, such that
So this would mean asymptotically, if we take any point, the set E sort of is a kind of cusp.
I should say something about the geometry of E. You see, of course, it doesn't say anything if B is identically 0. But we said that it's not. We said that integral B d mu So here. So such thing should definitely say something interesting about set E. So if E is just a segment, such B is not very difficult to find. So you shouldn't take just identically 1 on the segment. B is identically 1. We'll have logarithmic blow-ups here. It won't be bounded. But if you take the function B like that, with smoothing the ends, it will give you such a bounded Cauchy transform. It's a little bit more difficult to see that if your E is very tiered apart, it's very, very like that, but it lies on a rectifiable curve, you still can have such B. It's not trivial to see. I cannot draw the picture of this B, but it exists. And what theorem says in this case, that whatever is your E, if this is true, then there exists a rectifiable curve which you can go through catching a positive piece of E. So it's like you're a bandit, you want to rob banks. Banks are in these points where E is, and you can have a finite amount of tank to rob non-trivial amount of banks. So it's like a traveling bandit problem. So if this is true, then your traveling bandit will have some money after his travel, spending only finitely many. Why finitely many? Because it should be rectifiable. Finitely many gas.
Or you have enough money to raise as charity.
Now, when n is bigger than 1, the picture is exactly the same.
Can you seem possible other information of other part?
Because the other part is necessarily has no information, because you see, by how I formulated that, I didn't say that support of B is equal to E. It can be just 0 on a piece of E. So then it has no information on of course, if I say more about B, I will say that actually not only it will be able to rob non-trivial portion of banks, but that he will be able to rob all banks. But this requires a little bit more to say about B. Then it becomes not traveling bandit problem, but traveling salesman problem. You have a set E on the plane. So when you can connect all this by a finite length. So it's not a combinatorial problem like in graph, because these are just points on the plane, not on the graph. But whether you can connect them by connected graph of finite length is a valuable question. And one of the theorem in the future will be like that. Okay, so for n equals 1, the same picture, only you cannot interpret it as any bank robbers, because manifold now, like for example, n equals 2, so our main measure is H2, so manifold will be 2-dimensional, and you cannot say that. But still the same thing, you can draw a 2-dimensional thing through your E capturing non-trivial piece of E. So this is what theorem says.
I don't really understand the connection here with this connectedness of the set.
It's the main thing. It's why, well, this, which I draw, it's a great set. This counter set is H1 like that. Not this set, but counter set, which you consider. But you will not be able to put it on a connected thing. Or if you can put it on a connected thing, this connected thing will have infinite length. So that's the main thing, that we can put it on a thing which is connected and has finite length.
Also a question. Do you have by some mean a way to define pointwise traces on the set E?
It's a very, very good question. Let me, let me,
Because I have the feeling that
yeah, let me even answer it. Because if you already establish that this boundedness gives you this geometric picture, and as I said, if you know a little bit more, it gives you this geometric picture, on such guys, you can define, how you said,
pointwise trace.
pointwise trace, Hn almost everywhere. But that's absolutely crucial thing. You can do it only after you prove this theorem.
And now my second question. Is this somehow meaning that your function is locally a special function with bounded variation? Because this would have as a consequence exactly what you say, that there is a non-trivial jump set, and that set that you showed E prime would be the jump set.
Well, first of all, E is not any kind of jump set. You remember I emphasize everywhere that function U is Lipschitz on the whole plane. Or if you don't like this, let it be Lipschitz outside of E. Okay, but I will require that it will be continuous on E. So otherwise, theorem can be true, can be not. I don't know the answer.
Good jump, gradient U jump.
Yeah.
Oh, a gradient of U jump, that's true. Right. That's true.
I think maybe just remark, I'm not sure if I'm right here, but so what you mean is probably the derivative of the function.
Yes, give me the
And
trace.
they have traces which are equal with the opposite sign from left and right.
Again, guys, sides can be defined only on such thing.
Yeah, right.
This guy has tangent plane, tangent line at almost every point. This doesn't. So it doesn't have any sides. So before defining the sides, before defining the jump, you have to prove that you have this.
Yeah, sure.
Okay, so that was reduction. So now pay attention to this thing, because I will erase it now, but it will be the main player in the future. So on the plane, it's this kernel. But in space, it's this kernel. Now, how fast it blows up? So first of all, you should think about x minus y, x minus y, x minus y, x minus y. And blows up means x becomes close to y. Like with kernels, you always have difficulty when x becomes close to y. And how fast? First degree in the denominator, n plus 1 degree in the denominator. So the blow up is n. So singularity of Rn x minus y is minus n. So this singularity is minus 1. And measure so how fast it decreases when you make smaller and smaller scale. Typically, typical doesn't mean that it's true, but typically that's true. And so they match each other. And so if you try to consider this operator with respect to this measure, it means that there is no absolute convergence. So it's a singular integral. You cannot put absolute values anywhere inside. it's not even clear what does it mean if you start with E and end with E, what it means, because you cannot define the integral. So it's a singular integral. So far it's singular integral. Now let me continue. Singular integral operator. So what does it mean, singular integral operator? We take a function on E with respect to this measure, and we want to send it to here, but we also want to finish with the function from here. But as I said, we have difficulty to put x back on E. So what we do, I mean, yeah, what people do always. They make regularization, they integrate over y bigger than epsilon. So it's like a family of operators. And then every guy is very well defined, and you may ask the question whether this operator is bounded, but because everything E is compact, epsilon is positive, that will be a trivially bounded operator. What you want, that bound will not depend on epsilon. So if bound does not depend on epsilon, then we say that Rn is bounded singular operator. So if bound does not depend on epsilon, there are several other ways to regularize. There are millions of ways to regularize, and it has been all actually proved that all regularization are equivalent. So if it bounded like in one sense, it will be bounded in another sense. And so we come to the realm of singular integral operators. And these are operators which have a certain type. They are not just living by itself, because they have a certain, they are in a certain class. So this is a singular integral operator of Calderon-Zygmunt type and of singularity minus n. It doesn't matter what Calderon-Zygmunt type means. Just means that it's it's the least singular operators out of singular operators. So theorem 3. So it's not even so much interesting theorem 3 that you can reduce theorem 2 to theorem 3. So theorem 2 says that you have a harmonic function with bounded gradient. And theorem 3 says that if Rn is bounded, and mu is, as always, then E is n-rectifiable. So the most funny thing is that as soon as you prove theorem 3, you prove theorem 2. So there is a reduction from the existence of Lipschitz harmonic function to the boundedness of the singular operator. So maybe I will explain the reduction a little bit later. But now there is one more reduction.
So the operator norm being bounded, that correspond to the gradient being bounded.
So the reduction will look like that. Okay, we have this b d mu such that integral Rn x minus y b d mu is bounded. That's given. That's what we know in theorem 2. So then, and this is highly non-trivial then, there exists E prime of positive piece such that Rn is bounded. So from the boundedness of operator on one function, we should conclude that there is a piece such that operator is bounded on all functions. Now, this is very, very highly non-trivial thing. So this is this ACTA 2003. And actually several other things. Let's talk about this in 2 minutes, because I want to make the last reduction. So to prove theorem 3, one needs to prove theorem 4 and then reduce it to theorem 4. So theorem 4 is exactly the same, but you know more about E. Suppose E is good in this following way. Suppose that for any x on E, and for any r like that, you know that this Hn, our Hn measure on this E satisfies Alfor's irregularity condition. So with two constants, positive and finite constant, we have Alfor's regularity. And also, you also know that Rn is bounded. So we have to conclude from here that E is unrectifiable. So it's like theorem 3 plus one more condition. But because there's plus one more condition, a slightly better situation, we actually can conclude a little bit more, that E is uniformly unrectifiable. I explained what is unrectifiable when you can cover it by countably many guys. Uniformly unrectifiable is the following, that in every scale, you take a small ball of any radius centered at your set, then you can find the rectifiable curve inside the small ball, which captures 50% of your set E inside this ball. And 50 doesn't depend on scale, place, anywhere. So first of all, one should prove, but it's an easy proof, that uniformly rectifiable also means rectifiable. But it implies rectifiability. But it's an easy part. Okay, so this theorem 4 it has a very interesting story. So when n was equal 1, so it was proved by Mattila, Melnikov, Verdera. I think it's, I forgot, it's around 2000. It's their paper in Annals of Mathematics. But for n bigger than 1, it was known as the David Semmes problem.
That should be 96.
Oh, 96, absolutely. You're right. So David and Semmes in the 1991 or something like that wrote 2 books, actually, each devoted to this theorem. And in both books, it was not proved. But they made like 30 equivalent conditions or more, which would be equivalent if we prove them, then theorem will be proved. So they didn't even know the answer for n equals 1. But then for n equals 1, it was found in this paper. Why such a big difference between n equals 1 and bigger than 1? It's because for n equals 1, a certain notion which is called curvature of Menger's curvature of measure was used. So it turns out that if operator is bounded and n is equal to 1, you can conclude a geometric thing, that curvature of measure is finite. A curvature is a beautiful thing. What is a curvature of 3 points? Take the unique disk, which has this on the circle, and 1 over radius is the curvature. And now you know what is the curvature of the measure. You should average it over 3 times d mu x1, d mu x2, d mu x2. Because we are analysts, we always average L2 norm. And then you take a square root. So for n equals 1, it has been proved, which is a certain super miracle, that if operator is bounded, then curvature is finite. And if curvature is finite, it means that radius is very large for many, many triples. Because then 1 over r is small for many, many triples, and it allows it to be finite. The curvature to be large, they should be flat. So we come to the realm of discrete analysis, counting how many flat triples we have, and with extremely non-trivial consideration, which includes another paper in Annals of Mathematics, you can see that it has a geometric consequence. But it was because of this finiteness. And this finiteness, by miracle, followed from boundedness of the operator and the fact that n is equal to 1. And it has been proved that if n is bigger than 1, the boundedness of the operator does not imply the finiteness of curvature.
Measure curvature will not be defined in higher dimension? So the curvature, measure curvature cannot be defined in higher dimension?
For any measure, right? But here our measure is H1.
Okay.
Here it's H1, this is what is important. Yeah. And so it was a big roadblock. And so because curvature was not available, and this has been recently done by the second NTV, so it's Fedya Nazarov, Xavier Tolsa, myself. It was just recently done, so this was done. And then you reduce theorem 3 to theorem 4. For that, you need to kind of fill the gaps in E. E is not Alfors regular. It has maybe this property, which is also not true. But the major difficulty is that it drops very much. So you need to fill the holes, which is not a trivial task. So I don't want to talk much more about that. And I don't want to talk about the proof of this, because it's absolutely separate subject. So maybe one word that, of course, we get rid of curvature in proofs. We don't need curvature. It turns out that this invention of curvature, which was a miracle, is not needed, even for n equals 1. You can work with a simpler, more rough quantity and come to the same conclusion. And so maybe a word about this reduction. So why, if we have the boundedness on one function, but you see it's a boundedness of what type? Function was L infinity, result is also L infinity. Just one function. Why we have the boundedness of the operator? So it's actually not super strange, because there is David Semmes theory of Calderon-Zygmund operators. In other words, T1 and TB theorems. So what this funny abbreviations say? It's a certain class of theorems. So T1 says, for example, the following. If T is a Calderon-Zygmund operator, we are in Rn plus 1, and we work with measure, well, let it be Rn, and we work with measure N. And if we put, so this is mu n, Lebesgue measure, integration over space. We put here 1, and it turns out to be a bounded thing. Then operator will be bounded. No piece, nothing, just it will be bounded operator. So it's sufficient to check the boundedness of operator on one function, and it will be bounded. It's amazing, but of course it uses Calderon-Zygmund structure and things like that. And of course I'm cheating a little bit, because one needs also to check this. It says conjugate operator. Well, has one more condition, which is not important here. For antisymmetric kernels, our kernel is antisymmetric, third condition doesn't appear. Well, TB theorem says the same thing. But now you put B, but then you should say that B is something like 1. Something like 1 means it's accretive. Accretive means exactly this, but for every ball. It's like if the function is bounded from below, it's of course accretive. But this, by the way, I'm sorry. It's a different condition. And, but it shouldn't be bounded from below to be accretive.
So you need B not to be 0 in the right set.
It forbids it to be.
Exactly.
Yeah, but
capture
for example, if real part of B is bounded away from 0, this will be satisfied. But you see, we have it only for one B, for the biggest one. So our theorem is like TB theorem, which is non-accretive and not for Lebesgue measure. And you see, even if it's not Lebesgue measure, if it's just any measure, but doubling means that the measure of the double ball is bounded by some constant measure of the ball. So even this generalization was quite non-trivial. It was done by Michael Christ. But our measure, in principle, doesn't have this property. You see, in theorem 3 it doesn't. And in this reduction it doesn't. And so it's not doubling. So we have non-accretive, non-doubling TB theorem. And we pay the price by the fact that we have to choose a piece. But this is a non-trivial piece, fortunately. And then we'll go to theorem 3. We'll go to theorem. Thank you very much.
Okay. Thank you very much.
Are there any questions?
Yeah, in the first theorem you state, the fact that you have all the space is essential. So you have just a
Absolutely, yeah. Thank you for the question.
problem.
Yeah, absolutely. Yeah, it's a local theorem, of course. It doesn't have anything to do with the whole space. If we if we have a ball and set E is inside, we just say that function is Lipschitz in the ball and harmonic in the ball minus E, and it's not harmonic in the ball. You should say some non-triviality. Before, to say non-triviality, we say U is not 0. And now you should say some way to say that it's non-trivial.
I can give you an example that I'm wondering if it's applicable, your theorem is applicable to this example. Think about the least superharmonic function lying above a very thin obstacle. So it's the thin obstacle problem.
Yes.
And as a consequence, of course, there is a is harmonic except in the coincidence set. And the conclusion, if you can apply your theorem to this problem,
How about gradient?
it is well depending on the obstacle. But if suppose that obstacle is not too bad, say it's a C1, C1. It's Lipschitz function, I think.
But then it will make no sense because we are proving that through our obstacle we can drive by a Lipschitz thing. It's if it's already Lipschitz, so then there is nothing.
No, it's global Lipschitz. However, the function is not harmonic when there is contact with the obstacle.
Right.
Okay, and so globally there is a positive measure concentrated on the coincidence set between the solution and the obstacle.
But obstacle already is a Lipschitz thing. So it becomes an empty theorem. From the very beginning, we know that E lies on the Lipschitz thing. What we are proving that there exists a piece of E which will lie.
Think about an obstacle that likes that. So
okay.
contact is not equal to all. Yeah. You see, so it may be.
Oh, I see.
So this
I
is
see.
some kind of free boundary problem.
I
It's
see.
the obstacle problem, obstacle thin problem.
I see.
And if we can apply your theorem to this problem, it's a very interesting conclusion. That means that the free boundary is essentially rectifiable.
Yeah. That's what I'm looking for.
And
If
this
you
should
can.
be really quite interesting because there is partial results not by Caffarelli, but they are local results, and you have a global result for the thin optical problem. It looks like it's applicable, which is very, very interesting.
Yeah, exactly.
If it's true, what I'm saying, I'm not sure.
Well,
Check it.
let's talk about let's talk about that tomorrow or today later. Okay?
Discuss on this.
I have a question about this. Double. You said you don't have doubling. Is that in cases? Excuse me. It's cases when the Laplacian becomes zero extension, and you don't get doubling.
No, unfortunately not. You can have an awful situation. You can have positive H1 on some E, which will have lim inf almost everywhere. So you have absolutely non-trivial measure, H1, which is so awful that its lim inf is zero almost everywhere. And outside of this E, you may ask whether you can have a Lipschitz harmonic function. And the answer, you are right, is no. You cannot. So Lipschitz harmonic means goodness of the set necessarily. These are awful sets, and there will not be Lipschitz harmonic function outside, no, except zero. Yeah, so you are right. So such. But you see, it's suppose you have a mixture. Suppose you have a mixture of this bad set and some better sets and another set. So how to separate them? You cannot separate them. So you cannot say that you can always extend into the bad set. Or maybe you can, but I cannot prove it. So in this case, yes, you can, if it's only bad. But if there is a piece of good, maybe it makes it better, so I don't know.
Other questions? Oh, let's thank our speaker again.